Yes, thank you very much for the introduction. I'm very happy to start with this seminar series. So today I'm going to talk about quantum technologies in the Anthropocene. I think it's very good that I start the series in the sense that in the end, as you'll see, I won't talk much about the details or even quantum technologies at all in a certain sense. But I'll try to offer a perspective about science and technologies and what we call values in science and technologies in the context of the big climate challenge, environmental challenges, and what is called the Anthropocene more broadly. That's the idea. And hopefully providing a framework for the discussion afterwards and the other talks in this series. So climate change is often referred to as the defining issue of our age. Here is, I'm not going to talk about the details of climate change or even the Anthropocene, just giving you a few quotes, just setting a little bit the stage that you probably, of course, all know. Here are a few very strong words by the UN Secretary General at a high-profile meeting, the COP27, almost 2 years ago. Greenhouse gas emissions keep growing, global temperatures keep rising, and our planet is fast approaching tipping points that will make climate chaos irreversible. We are on a highway to climate hell with our foot still on the accelerator. It is the defining issue of our age. It is the central challenge of our century. So I think this is clear. Here, the Secretary General defines, and he's of course not the only one, climate change as the defining issue of our time. But there is a sense in which climate change is only a kind of an aspect of a set of challenges, even possibly existential challenges. Here is a quote from the Secretary General to another high-profile meeting, the Leaders Summit of the United Nations Biodiversity Conference. In 21, we are losing our suicidal war against nature. Our 2-century-long experiment with burning fossil fuels, destroying forests, wilderness, and oceans, and degrading the land has caused a biosphere catastrophe. Humanity's reckless interference with nature will leave a permanent record, just as today's scientists study the traces of previous extinctions. We are well into the Anthropocene extinction. The rate of species loss is tens to hundreds of times higher than the average of the past 10 million years and accelerating. So again, very strong words, but here what is interesting again is that the focus is not only on climate change, but as you can see, much on a wider, broader set of issues. And one way to characterize this is using this concept of Anthropocene. It's a kind of very broad concept, but it tries to capture this idea here that I want just to discuss, is that climate change is only one aspect of a larger story, in a sense, involving disruptive human interferences in fundamental life support planetary processes. This has been captured typically by this image here of this framework of planetary boundaries, typically within the framework of Earth system science, where a number, typically here 9, fundamental planetary processes have been identified, and for which kind of thresholds you see this green space in the center, defining a safe operating space of thresholds in these 9 planetary processes, beyond which we are not supposed to go in order for a certain, again, life support processes to function as we know them. That's a little bit the idea. This kind of framework raises a number of challenges, but you see the idea here. I want to emphasize that, again, climate change, as you can see here on the top, is one dimension of these here, typically 9 planetary boundaries. We can define other boundaries, probably. There are different things to be discussed about this framework, but that's the idea I want to convey here. And navigating now this kind of new regime in this sense of drastic human-induced global environmental disruptions may require new forms of scientific knowledge that seriously address the deep entanglement of natural and social processes or dimensions at the heart of what is called, again, the Anthropocene challenge. Anthropocene, again, is a term coming from geology, stratigraphy. It's a proposal which has been, by the way, rejected recently to define a new geological epoch. But here it's rather this idea of this new regime of drastic human-induced disruptions to planetary, fundamental planetary life support, planetary processes. And in this sense, this concept is still extremely interesting. Now, the focus of my talk is a little bit trying to raise attention about the role of science in general, of technologies and quantum technologies in particular, in this context of these climate, environmental, Anthropocene challenges. How can we understand the role of developing quantum technologies in the face of these huge environmental challenges? And I'll talk a little bit about the link between, which is maybe not obvious, between quantum technologies and climate change. So one dimension of the set of challenges I've mentioned. And then I'll try to take, rather than going to the specifics of the application, the possible application of quantum technologies to climate change. And I think some of them will be discussed in the subsequent talks in this series. I'd rather take a philosophy of science perspective on the question of values in science and technology, what is called non-epistemic values. So I'll try to offer the philosophy of science perspective on this question. And I'll take typically the example on which I've been working a little bit of climate science and modeling. So the role of values in climate science and modeling. And the idea is to try to draw some lessons then for science in general and for technology and quantum technologies in particular. We'll see together that one of the main challenges when it comes to these questions of values in science and technology is the question of value management. So once the role of values is acknowledged, the question is, what do we do with them? How do we manage these values in science? Given that it's very difficult to get rid of them in a certain sense. And then trying to go forward from there, I'll try to defend, in a few words, an idea of a kind of justice-oriented science, or try to suggest to what extent would be possible, desirable, to include these certain non-epistemic values in the sense of developing a justice-oriented science and technology. And I'll take a recent example of an interesting development of the inclusion of a justice perspective in climate science and in particular Earth system science in this framework I've just mentioned of planetary boundaries. And then I'll come back at the end to quantum technologies and trying to discuss a little bit with you also in the Q&A about possible implications of all that, of this value question for the development of quantum technologies and in particular, of course, sustainable quantum technologies. Again, I'm not going to talk so much about quantum technologies, but I think the other talks in this series will be talking about the specifics of quantum technologies and typically the relevance, the applications of quantum technologies for climate change and other sustainability issues much more than I will do. So I'll try again to offer a kind of broader philosophy of science perspective on the question of what I call here non-epistemic values. I'll define this just in a minute. Now, just about this notion of sustainable quantum technologies. And again, before starting here, maybe, I just want to mention there is a whole field also, philosophy of technology more generally. I'm not specialist on that. I'll really try to offer here the kind of even broader philosophy of science perspective on the question of values, which applies, I think, to science and technology. There's a kind of continuum here in the discussion about philosophy of science and philosophy of technology proper. There is an interesting recent paper here by a bunch of science studies scholars and scientists on the quantum technologies and society here. And they try to argue, one part of the paper is trying to argue for trying to convey quantum theory and quantum technology in a clear way. This is perfect, it makes perfect sense. And then they try to argue that quantum technologies and the community needs to engage here transparently with society and address social uncertainties, what they call social uncertainties. And what is interesting is they argue that this has to be done in order not to face problems, what they call fiascos of implementation at the interface of science and society. And then they define a number of desiderata, in a sense, for the development of quantum technologies. And typically here are two of them responsible. So this development of quantum technologies needs to be attentive to what they call long-term effects and unintended consequences. There is this criterion of being meaningful for society. So typically addressing a variety of societal needs, hopes, and concerns. And I think what is interesting here is that this offers a kind of broader notion of sustainability or sustainable quantum technologies, which encompass both the sustainability applications, so application of quantum technologies to sustainability issues, like, again, climate change, and the question of sustainable development of quantum technologies themselves. I think Dakota Root, you're going to discuss this distinction a bit more in your talk, and the other talks in the series will also discuss typically either applications of quantum technologies to sustainability issues or to the sustainable development of quantum technologies, typically in terms of energy consumption of quantum technologies and so on. But here, what I want to point out is that there is a sense in which sustainable quantum technologies is even broader in a certain sense than these distinctions. But again, I'll come back to this. Now, about the link between typically quantum technologies and application to sustainability issues, I'll take the example of climate change. There are a number of very high expectations out there about the relevance of quantum technologies for climate change related issues, be it in the energy sector or even in climate modeling itself. I'm not going to talk to go into the details. Again, I think one of the talk in this series will probably go into more detail. Here is an example of a kind of white paper about the possible relevance of various types of quantum technologies for climate change related issues. And here are big, bold claims about the possible relevance of quantum technology, typically here quantum computing, and in the context of climate modeling, typically. But it's of course much broader. It's about quantum simulation, of course, quantum optimization questions, quantum sensing, data, and so on, and in the energy domain, questions about carbon capture technologies, so different types of materials, technologies, but also crucially, as I said, in the context, and that's what I'm going to take as an example of climate and weather modeling, so climate modeling and weather forecasting, where of course there is a demand for high computing power, and the prospects of getting the power of quantum computing is of course very interesting in this domain. Now, the worry I'll try to address via the philosophy of science discussion about values in science. The possible worry here is that despite these possible sustainability applications, typically here, as I'll take as an example to climate modeling of quantum technologies, these quantum technologies may fail in a certain sense to be sustainable in a kind of broader sense I mentioned before. So going beyond just applying to sustainability questions without specific care. So I think this there is a need here for very specific attention to questions typically of values in order for these applications to be sustainable in this kind of broader sense. So that's a little bit the idea of my talk. Now, more generally, I'll take a very general perspective on this question of values in science and technology. And this is a central topic in philosophy of science and neighboring disciplines like science and technology studies typically. And there is quite a long tradition, for instance, with figures like Kuhn and others, either Douglas and other people recently working on this. It's still a very lively ongoing debate in philosophy of science about the role of values in science. What do we mean by values? There is this distinction between epistemic values and non-epistemic values. By epistemic values, typically, it is understood values that enhance the likelihood of a theory or model to be true in a certain sense, or advancing knowledge or understanding. Typical examples in the literature are empirical adequacy. If we take as a nice epistemic value of a theory or model, if it's empirically adequate, if it's consistent with a certain body of knowledge, if it's explanatory powerful, if it's simple, fruitful, and so on. These kind of values are typically of the epistemic type, because again, they enhance the likelihood of the model of the theory to advance knowledge in a certain sense, or even to be true, again, in a certain sense to be defined. That's a little bit the idea of epistemic values. Non-epistemic values would be then social, economic, ethical, political values. So the kind of values that are not epistemic in this, in the sense I've just mentioned. Of course, there would be a big discussion here to be had about this distinction, but that's not the aim here. But there is a kind of, I think, broad consensus in the literature that to various degrees, at various levels, again, depending on the science, of the technology, and so on, that these non-epistemic values are part of science in general. Again, to different degrees, depending on whether you're looking at fundamental physics or whether you're looking at more applied science. But in general, there is a consensus that it's very difficult to go for this kind of value-free ideal of science. So a science which would be completely where these non-epistemic values would play no role at all. And there is even a question about, first of all, whether this very distinction between epistemic and non-epistemic values makes sense in the first place, and whether, again, completely rid of these non-epistemic values in science would be desirable in the first place. And this is especially true in domains with strong societal relevance, typically with environmental science, climate science, and so on. Of course, there is an obvious worry here about biases. Once we accept the role that certain non-epistemic values play some kind of possibly irreducible role in science, there is the obvious worry of biases. And then the next worry of which values could play a role in science, if at all. The question of value legitimacy in a certain sense. And so the big challenge, and this is really part of the ongoing discussion in philosophy of science and beyond, is about what is called value management. So how can we manage in legitimate way for certain values, non-epistemic values, to play a role in science? And of course, there's the question of epistemic integrity against this worry of biases. I'm not going to talk much about epistemic integrity. There is a lot of work on this. I think it's related to what I'm going to say, but I'll try to focus a bit more about the question of value management in this talk. But of course, in the discussion, we can talk also about epistemic integrity. But I think it's good to keep in mind this question of epistemic integrity as well. So there is these two aspects: how to manage values in science, and of course how to have a high level of epistemic integrity for our science. I'll take as an example, as I said, the example of climate science and modeling, because it's a very interesting example. It's related to the question we want to discuss in this series on in the context of climate environmental issues, and it has been again studied by philosophers of science. And what is interesting also is that it is starting to be acknowledged by climate scientists themselves. Here is an example with this Nature Commons paper, and also in high-profile reports like the IPCC reports, the latest report, for instance, from the Intergovernmental Panel on the Climate Change, the ER6 reports. So, and again, there are a number of articles, of research papers showing that non-epistemic values, again, in the sense I've defined before, play different roles at different levels in climate science and modeling. When setting the aim or the purpose of typically of the modeling exercise, when constructing and developing, assessing models, for instance, in the parameterization process in climate modeling, in defining model ensemble uncertainty, in extreme event attribution. There are different examples in climate modeling and in climate science and modeling where the non-epistemic values have been identified. And what's interesting here is that there are clear cases of non-epistemic values influencing the internal practice of science against, again, this ideal, this value-free ideal. But what's interesting is that it has been highlighted that it doesn't diminish what I've called before the epistemic integrity of climate science or climate modeling. And again, there is an argument that even to the contrary, possibly, that this is the title of this paper, The Value of Values. These values need to be acknowledged, and maybe they are even to a certain extent desirable to us for a given certain purpose of science. I'll just give an example briefly here about the role of values when setting the aim of science, of scientific endeavors or modeling endeavors typically, and in the context of model construction and development. I won't go into too many details, but just to show you a little bit how it goes. Here are examples where non-epistemic values can play a role, typically first when defining the climate variables. Here's the context is climate modeling. So what kind of variables or processes or thresholds do we define in our modeling exercises? Typically temperature, precipitation, what kind of threshold, these famous 2-degree targets. These are typically, there are a number of choices there to be made to focus on temperature rather than precipitation in certain monsoon systems, and to set, for instance, these 2-degree targets, which are influenced by certain economic, geographical, social considerations that are not directly only purely empirical. Typically, whether you want your models to focus on certain regions, the Sahel, the Western Europe, and so on, these are choices that are influenced by, again, non-epistemic values and are not, of course, purely empirically constrained. Here's a quote from a paper discussing this about, again, climate modeling. None of the current generation of general circulation models, so these are a type of climate models, was built in Africa, for instance. And the relevant processes operating there have not always been the first priority for model development. Another question is about the temporal and spatial scales you're focusing. So typically multi-decadal, multi-centennial. So medium term or long term. And again, these are questions that are typically value influenced, whether you focus on global mean, high resolution, and so on. I won't go into the details. But again, another point is whether you focus on worst case scenarios, extremes or not, again, are typically influenced by certain non-epistemic choices. Here is an example of the latest IPCC report, so the Intergovernmental Panel on Climate Change report on the physical basis of climate change. Here you have a synthesis of the assessment of observed change for hot extremes, and here heavy precipitation. I won't go into the details, do not matter, but what is interesting is that you have the world here divided in a number of regions, and you have an assessment of the agreement, high, the confidence, and high, medium, or low, and you have decrease in the color, and you have these gray regions where you have limited data and or literature. And typically, if you take here for the hot extremes or here for the heavy precipitation, most of them are in the global south. And this is not, again, if you remember the quote from the previous slide, it's not because the physics there is different or that's the processes there are more complicated. They are maybe different to a certain extent, but it's also because there's a lack of data, and this is the result of certain lack of focus and a certain lack of interest in a certain sense of certain choices that have been made, and again, not driven only by empirical considerations, but again, by certain non-epistemic values. And again, as mentioned in the previous slide, the fact that most of the modeling centers, big modeling centers, are based in the global north here has typically possibly an impact, as shown here in this slide. Things are, by the way, slowly changing. Another example, quickly, I won't go into too many details. It's not much about quantum technologies, but again, there are expectations that quantum technologies will help when it comes to climate modeling. Typically, there are choices to be made about what processes to represent and how, because we cannot represent everything, and this is the role of parameterization. And here, whether you want to optimize certain variables over others, certain regions over others, is typically influenced possibly by certain non-epistemic, what I've called non-epistemic considerations. There is the question of calibration or tuning, adjusting poorly constrained parameters in your model such that discrepancies between model outputs and selected observation are minimized. But again, which observation are you going to consider for your calibration procedure? Whether you want to optimize ocean heat transport, for instance, which is relevant in the North Atlantic, which is relevant for Europe, or whether you want to optimize tropical convection, is a choice which is typically influenced by certain non-epistemic geographical value consideration. There are here epistemic trade-offs to be made in these optimization procedures, and this again will not change once you include quantum computing in the picture. These epistemic trade-offs will remain. So there is a need to acknowledge the role of values. These were just a bunch of examples. There are many others which have been quite systematically studied now. And the challenge now is about value management in this context. As I said, there is an ongoing debate in philosophy of science and in neighboring disciplines about how to best manage these non-epistemic values in science and technology. There are different strategies, proposals. Here is one I'll suggest, which is based on a kind of compromise between different proposals found in the literature. This has been suggested by a philosopher, Kevin Elliott, And there are three conditions suggested here. The first one is transparency. So here are quotes. By transparency, he means scientists should be as transparent as possible about their data, methods, models, assumptions, so that others can identify the ways in which their work supports or is influenced by particular values. So that's the first conditions that he suggests. Another one is what he calls representativeness. Scientists and policymakers should strive to incorporate values that are representative of major social and ethical priorities. Again, he's not the only one as suggesting this. These are kind of combination of various proposals found in the literature. And the third one is what he calls engagement. This condition focuses on generating engagement between different scientists, community members, and scholars from a range of different fields. Here, the idea is in particular to promote a kind of diversity. So you see here three conditions for guiding value management. But of course, in the context of global environmental changes like climate change or the other dimensions of the Anthropocene challenge, there are a number of difficulties. I won't go into all details here, but just to give you an idea of the kind of difficulties that one encounters when one tries to discuss seriously this question of values in these global contexts. Take this condition of representativeness. So again, scientists and policymakers who strive to incorporate values that are representative of major social and ethical priorities makes perfect sense. Typically, one way to articulate this is in terms of representativeness of stakeholders' values secured by certain democratic mechanisms, typically deliberative democratic mechanisms. So you identify stakeholders, and then you put in place certain deliberative democratic mechanism in order to identify the values, and then the important values, and then you try to incorporate them in your typically modeling exercise. This has been studied by Parker and Lusk, for instance, for certain types of climate services. But of course, in the global context of global environmental challenges, like in the different dimensions of the Anthropocene, it seems to be extremely challenging to first identify the relevant priorities and values, of course, and even before that, the relevant stakeholders to engage with when we're talking again about a kind of planetary level, like in the case of climate change. Just to give you an example, it seems really non-trivial to engage genuinely with the various indigenous or other subaltern, what is called subaltern in the literature communities around the world. This raises again a number of issues there which need to be discussed and partly already discussed in different domains and disciplines, like again decolonial literature. But what I want to highlight here is that there are a number of difficulties about trying to navigate possible value conflicts and trade-offs, which will need to be made once we try to be serious about this value in science question at a planetary scale. In particular, when it comes to power structures and what is called epistemic injustice, for instance, again related to decolonial questions. But again, here are just very superficial remarks, but I hope you can see the importance of treating this question of values in science very, very seriously. And I think one way to to go forward on these on these questions, which is also starting to be discussed a little bit in the literature, is trying to to acknowledge this role of values in science and in technology, and now trying to incorporate them, focusing on justice consideration. And here, one key insight is to move forward on this value management question is the acknowledgements that scientific knowledge and technology, so scientific knowledge production and technology development, are never articulated in a historical or social political vacuum. They're always context and a number of normative dimensions related to the development, to the production of scientific knowledge and the development of technology. This has been, for instance, discussed by the science and technology scholars Razanov. And here is a quote from her. So how we acquire and organize our knowledge of the world is always entangled with ideas of how we should govern it. And she has also developed, she's well known for having developed a notion of co-production of knowledge, which typically aims to capture this idea of the normative dimensions of knowledge, of scientific knowledge production. So here, the intuition is that we may need to develop kind of justice-oriented or involve or include justice considerations to the production of scientific knowledge and to the development of technologies. And of course, here including quantum technologies. And there is a recent interesting example about this incorporation of a justice perspective in the context of Earth system science within the framework of planetary boundaries. Typically, this notion of planetary boundaries I've just mentioned at the beginning of my talk was developed in the 2010s. Here is one of the original paper on these planetary boundaries. So the idea is to define what they call a safe operating space for humanity. So you define a number of what is considered fundamental life support planetary processes of the Earth system, and then you define thresholds for these boundaries. Typically, when it comes to climate change, you define a threshold 1.5 or 2-degree threshold, beyond which you argue that it's not a safe zone for the Earth system to evolve, for humanity to strive in a certain sense. And then what is interesting is that recently, so there is an overlap in the authors here. Here is a paper, Nature paper in 2023, where so it's the same framework of planetary boundaries. So you want to define this safe space for humanities, this safe threshold for planetary boundaries, but there is this justice component now. It's about safe and just Earth system boundaries. So you'll define these physical threshold in a sense, and then on top of that you add justice considerations in order to define your threshold. So you have the physical thresholds, and then you qualify this threshold according to certain justice considerations. And typically, in this concept, in this case, they consider numbers or 3 justice criteria in terms of interspecies justice, inter or intra-generational justice. And then they tried, of course, to convert this into biophysical units. Typically, for the climate change dimension. They will argue that the safe space would be 1.5 or maybe 2 degrees, but the just threshold would be 1 degree, because beyond 1 degree you inflict a number of harm to a great number of people and so on. And these kind of arguments you can make for the various dimensions. So you see the details here are not important, but what is important, what I want to highlight here is that this is an example of science in the making, in a certain sense. These are mainly Earth, not only, but mainly Earth system scientists, climate scientists, trying to incorporate in their science a certain number of justice consideration. Of course, it raises a number of issues. The ones I've mentioned about what type of values, how do you manage the possible conflicts, the trade-offs which need to be made, interactions, and so on. And this needs typically a very strong interdisciplinary engagement. So there is a number of epistemic questions and possibly limitations and constraints to this move. But I think it's an interesting example. Now, final implication of all that for quantum technologies. Again, the aim, I think, as put forward in this seminar series, is trying to develop sustainable, or rather, in this broader sense, what I would call meaningful, in what has been called also in the climate science case, meaningful climate science, so meaningful quantum technologies. And this may involve more than, again, applying quantum technologies to sustainability issues, like the climate change related questions, or the sustainable development of quantum technologies, typically in terms of energy consumption of possible quantum computers, or about discussing their environmental footprints, which are, of course, fundamental questions as well. But what I want to highlight here in my talk is that the sustainability question, or this question of developing meaningful technologies, goes beyond these considerations. Again, the one worry, just quickly again, is about maintaining existing or creating even new inequalities and injustices by developing these new technologies. So in the face of the climate, environmental, Anthropocene, morphology challenges, I've tried to hint at the need of a new justice-oriented form of scientific knowledge and technologies. And all this is, of course, very programmatic, and it raises a number of challenges. But I think philosophers of science, scientists need to face this question and try to have a kind of critical reflection on this question of values in their work in the science and in the development of technologies. So in the context of quantum technologies, I think one first question is trying to identify, identify here, the roles of non-epistemic values in the development, because of course it's quantum technologies are in the making, are developing now, and then in the possible implementations. But I think this is very important to have a kind of reflexive, critical stance by the quantum technology community itself when developing these quantum technologies. So first, trying to identify the role of these possible non-epistemic values in the development of these quantum technologies, and then there are the questions of how to manage these values. And again, there are different strategies. I've mentioned that, being transparent and so on. And I'll just finish with this quote from a historian of science. So Jürgen Wren, he wrote this book about the evolution of knowledge. So it's kind of grand history of science, and he ends his grand history of science with these words: in confronting the Anthropocene, we should reorient the current knowledge economy towards a global responsibility. And this transformation will have to include the interlocking of multiple knowledge dimensions and critical engagement with the entanglement of knowledge with political, economic, and moral issues. These are the hallmarks of science in the 21st century. So thank you for your attention. And